Let's review what we have done so far. So we have succeeded in making two-point function finite up to order lambda r. Okay, so we have made two-point function finite up to order lambda r. Okay, remember lambda r and m r, they are finite parameters. Okay, they have finite values, and the lambda and m which you had in the original theory, they become infinite as epsilon goes to 0. Okay, that is what we have seen. So more specifically, at order lambda r, we had this contribution at one loop from the to the two-point function. So let me just write it. So if you look at the two-point function, this is to the lowest order, this just a propagator, and then you have this diagram and of course the counter term diagram also, and we made this finite, okay, up to order lambda. And of course there are other higher terms, higher in order lambda, but we haven't done anything for those. Okay, we have whatever calculation we did last time was for order lambda terms. So these are those terms. Okay, because here you have a lambda r, and this vertex, as you saw, is also lambda r vertex. Okay, it's a two-point vertex, but the order is of course lambda r. And we have found that to make this two-point function finite up to order lambda r, the constant, the renormalization constants, take these values. So z of phi was 1 plus the order lambda r term turned out to be 0. So it was 0. So it starts at then order lambda r squared. Okay, that term turned out to be 0. And then zm square we found to be 1 plus 1 over 16 pi square. Let's check. I think that was correct. Let me go back and see. This is correct. Okay, and also remind you that z phi, what is z phi? So you had the field phi in the original Lagrangian that we wrote as z phi to the half phi renormalized. Okay, and m we wrote zm times m renormalized, and lambda to be z lambda times lambda renormalized. Okay. These are, as I told you earlier, these are called renormalized field and renormalized parameters. And these ones are called Bayer parameters and Bayer fields. I guess I said this before, but I'm not so sure. So these are all Bayer quantities, and these are all renormalized quantities. Okay. And as you see that zm square is a singular, 1 over epsilon term is present here. So when you take epsilon going to 0, which is basically going to 4 dimensions, then m becomes infinite. Okay, so at the cost of making these Bayer parameters infinite, singular, okay, we are able to renormalize the theory such that phi r, mr, and lambda r are finite objects. Okay, so this diagram plus this diagram. Okay, so right now I'm not including the external propagators. Okay, these propagators are not included. You can put a cut, you can put this little text to indicate that. And you remember, this is what we had defined as minus I sigma. Okay, sigma is for the entire one particle irreducible diagrams. So I will put a subscript 1 to say that we are at the lowest order. Okay, and this is what we found last time to be I lambda r over 32 pi square 1 plus log of mu square over mr square. Okay, this is good because log should have in its argument a dimensionless object, right? Otherwise there is no meaning to the argument, and this is correct because you have mass dimension 2 in the numerator and mass dimension 2 in the denominator. So log has an argument which is dimensionless, and that is how it should appear. And then log of 4 pi minus Euler gamma E minus Euler gamma times mr square. Okay, and we know that how a 2-point function behaves. So this is one particle irreducible plus these other, okay, and they resum to give you I times p square minus mr square minus sigma 1 p square plus I epsilon, okay, times the residue. So you see that this 1 pi includes all order diagrams, okay, but here I am restricting to only up to order lambda r. That is why I put the subscript 1, the sigma 1. And to this order, the physical mass is given by, to any order, the physical mass is given by the 0 of the denominator or the pole of the propagator, pole of this 2-point function. So I should look at where the denominator is 0. So what is the value of p square for which this is 0, and that value of p square is the physical mass square. Okay, because that's the structure, right? You know, it has to go as I over times some residue p square minus m physical square. Okay, so I'm just saying that when p square is equal to mp square, the denominator vanishes. So that is why I'm going to take this denominator and put it equal to 0, and the value of p square for which that happens is the physical mass. Okay, so what is the physical mass in this theory? With these choice of parameters is p given by the condition p square minus m square minus sigma 1 of p square is equal to 0. Okay, so let's solve that, and it's easy because it's easy anyway, but also note that sigma 1 of p square is independent of p square up to order lambda. Okay, there was no p square dependence, and you know why, because this diagram doesn't involve an integral which carries the momentum p. So what do you get? From here you get that p square minus mr square minus lambda r over 32 pi square and the other factors okay, that is the condition we have. And when we solve it, you get that this is 0 for p equal to this object, okay, which means the physical mass mp square is mr square plus lambda r over 32 pi square mr square plus lambda r over 32 pi square log of mu square over mr square plus log of 4 pi minus gamma e mr square. Okay, that's the physical mass. So you see that to the lowest order in lambda or lambda r, physical mass is same as the renormalized mass. Okay, they do not differ up to at the 0th order, at the lowest order. Then there is a correction. So physical mass is different from the renormalized mass square. Physical mass square is different from the renormalized mass square by this order lambda r correction term. And of course, these are also the terms which are present. So this is the total correction. And right now, this result is in a particular scheme. It is called MS scheme. Okay, right? Because I have, in writing this, only subtracted a pole term. Right? Zm had only a pole term, only the singular piece, nothing, no finite terms. Okay. But as I told you last time, you could also subtract finite terms, meaning you could also subtract this one, which is proportional to lambda r, or any other term which you want to remove, proportional to lambda r. Okay. So if you remove log 4 pi minus Euler gamma e, then that result is called a result in MS bar scheme. So you see that the physical mass depends on the scheme, okay, which is basically which is equivalent to doing a finite field and mass parameter and this mass parameter renormalization and field renormalization by a finite amount. Okay. But anyway, let's just say that this is a particular scheme in which we are giving the physical mass. Okay, good. And also the result depends on mu, which is the renormalization scale. Okay, and also should again remind you, I think I told here, so fine, good. Okay, now a couple of points. So this diagram did not contribute a term which was proportional to p square, but as I told, it was very specific to this particular diagram. But in general, let's say, in general, you will have p square dependence, but let's look at a special class of diagrams that appear at 2 loop. Okay, so at 2 loop, we will have these kind of diagrams. So this is a 2 loop diagram. So you see, I'm drawing all the diagrams which are lambda r square terms. Okay, so this has 2 factors of coupling, so it's lambda r square diagram, and then you have this also. Okay, so what I'm doing is I'm drawing all the diagrams that contribute to the 2-point function at order lambda r square. Okay, so this diagram definitely contributes. This also contributes. Then you have this one that also contributes because you have a lambda here and lambda there. This is called sunset diagram in the literature. And these ones are called cactus diagram. Okay, they look like cactus. Okay, so these ones, of course, again do not depend on p square. These integrals do not carry the momentum p square, so the p square dependence is solely in the propagators. Okay, but these integrals do not contain. This one is the same situation. Whatever p enters in here never enters into the loop. Okay. Okay, and it just goes out without entering the loops, but here it will enter. So if I draw this diagram, maybe a little bigger. So let's say you put L1 here, L2 here, P you have entering here. Okay, so this will be P L1 plus L2 plus P. That's what will enter here, right? Okay, so now you see that when you write down the integral for this one, it will be what? It will be ddl1 ddl2, okay, these factors also, and then you will have I over L1 square, I over L2 square, and I over L1 plus L2 plus P square. Okay, I forgot to write mr square plus epsilon. Okay, and now you see that when you evaluate this integral, the result will depend on P square and mr square. Okay, so this is going to be a function of P square. So you get an dependence on P square which was absent in this diagram and at one loop. Okay, which means that the Z phi will be non-vanishing when you go to two loops. This is a two loop diagram. Okay, sorry, not Z phi will be not vanishing. Z phi will be having a contribution at order lambda r square. Okay, so there will be some order lambda r square term coming from these kinds of diagrams. Okay, so Z phi will have a non-vanishing order lambda r square contribution. Okay, let me go back a little. Yeah, you see Z phi minus 1, this term is proportional to P square, right? Because it is coming from the del mu phi term. The counter term had a del mu phi, del mu phi r, del mu phi r. Okay, so there is a P square dependence here, and you are going to generate such a term from here as well. Okay, good. So before I proceed with new things, let me just also point out that if you were to calculate a two loop, you will have to include many more diagrams, not just the ones which I have drawn. So let me draw them. So of course you will have the cactus, and then you will have this diagram. Okay, so all you have to do is take all the vertices that are present, okay, and connect them in all possible ways with these two external points, okay, which will give you the external propagators. So you can also draw, this is another diagram that is possible, okay, and then you have these vertices present, so you can draw one such vertex, connect them, and take this regular vertex. Then you can also have, okay, then this this is also possible, right? Because these are both, this vertex is order lambda r, so two of these makes lambda r square. And then also you have the following. So suppose you take this 4-point vertex. Okay, that's, you remember this is order lambda r square. Okay, let me show you. If you remember, how come it's not here? Here. You see this, we had this counter term vertex which had an explicit factor of lambda r, and because z lambda and z phi are 1 plus order lambda r terms, this thing contributes at order lambda r. So lambda r times lambda r, it's a lambda r square term. So this counter vertex is order lambda r square. Okay, and that is what I am using, because I am drawing diagrams which are correct up to order lambda r square. So this vertex, if I take, okay, and these are two of my external lines, then I can connect it like this. Okay, so this is another order lambda r square term that contributes. Okay, this will bring in z of lambda with it. Okay, 2 loops. Okay, good. So let's now try to make things finite completely at one loop for the 5-4 theory. So we have already renormalized the 2-point function. Okay, but the goal is that we should renormalize everything, all Green's functions, up to one loop. Okay, so if there is any function given, Green's function given to me, I would like to have a finite prediction up to order lambda r, or let's say up to order lambda r, up to one loop. Okay, so I have already done 2-point function, already renormalized, okay, by choice of Zm and Z lambda. Now let's go to a 4-point function. This is divergent. Now this object is divergent, but we still have Z lambda at our disposal that we have not yet fixed. Okay, so we can hope that a choice of Z lambda can fix or can kill the singularities that are present in the diagrams in here. Okay, so let's see what kind of 4-point functions we have. We have already learned that the general structure of a 4-point function is this, that you can write a general 4-point function. I should go to next page, I think. Okay, let's go to the next page. So a 4-point function or any n-point function, the general structure is this. You have corrections on the leg. Okay, and the big blob in the center is what is called amputated Green's function, right? That is what we have seen earlier. So if you look at this, then in terms of Feynman diagrams, you get such diagrams. Okay, I'm looking only at the connected diagrams. So you can have a correction here. You can have a correction here, or on here, or here. Okay, these are all possible diagrams. Okay, then remember, we should use all vertices, not just this vertex, but also the counter vertices. So you can also get this diagram. Okay. How do I remove this? Let's try it this way. Okay, this can be misleading, so I'll does it remove? Yes. Okay. And you can have this diagram. Okay, this is also present. And then let's call P1, P2, P3, P4. Let's assign momenta this way. So here also Okay, and similarly on all these other diagrams. And then we have P4, then you have P1, P2, P3, P4, and then you have so this is P1 and this is P3. So meaning P1 and P3 attach at the same vertex. So here P1 and P2 attach at the same vertex, P1 and P4 attach at the same vertex. This is the diagram in which P1 and P3 attach at the same vertex. This is not a vertex here. Okay, P4 and P2. Okay, this is not a vertex. So these are the diagrams. Is any other diagram missing? So these are all order lambda r square diagrams. There is one more possible, which is this, right? Because this itself is order lambda r square. So now you see that because we have renormalized a two-point function, and this part of this leg, right? This is a two-point function. Okay, this is another two-point function. Okay, but the divergences in this are cancelled by divergences in this diagram. Okay, so these two together cancel all the singularities. These two cancel the singularities. Okay, so they pairwise, the singularities are cancelled in this. Okay, so as far as these diagrams are concerned, they are finite, okay, because of whatever we did earlier. But these are one loop diagrams that contain divergences, and we have a counter term available to us with a parameter that is with a constant z lambda, which is still not fixed, and we will try to adjust that z lambda such that the divergences contained in these three diagrams, the sum of it is removed. Okay, so our goal is, so here let's write that these are divergent in UV, and our goal is to adjust z of lambda such that the pole, the UV poles are cancelled in the sum. Okay, so let's evaluate one of these, all of these diagrams. So let's evaluate this. I'm not going to write the external propagators because they are common in all these diagrams. Okay, so see, I could write the external propagator here, I over P1 square minus MR square plus I epsilon, and similarly for these four. But that's the same here. Okay, so you can factor that out, and whatever remains is coming from the integral in this loop. Okay, and the z factors and everything else in here, and that is what I should arrange. Okay, so let's look at this one, P1, P2. So these are the momenta that enter. Then you have loop momentum L, and this is L plus P1 plus P2 flowing in this direction, P3, P4. Okay, and the expression is, let me first write down the propagators. So d4L over 2 pi sorry, not d4, ddl over 2 pi to the d I over L square minus mr square plus I epsilon L plus P1 plus P2 whole square minus mr square plus epsilon. Okay, we have two propagators carrying the loop momenta, and this is here. Then I should write down the vertices minus I lambda r over 4 factorial. Okay, there are two of them, so square. Then the combinatoric factor. Okay, so let's check what that will be. So you have these two vertices, and I have these 4 external points. Okay, so P1 can connect to any of this and this, right? So that's 8 possibilities. Then this guy should connect only on this vertex. It cannot go to that vertex because that will be a different kind of a diagram. So there are 3. And this one can go to any of the 4. This one can go to any of 3. Okay, I should have any of the 3. Then this can go to any of the 2, this and that one can go to only this one. Okay, 8 into 3 into 4 into 3 into 2 into 1. Okay, which is basically 4 factorial. This is 4 factorial. Okay, and the reason you have 1 over 4 factorial here is precisely because you get a 4 factorial. So that cancels, times 1 over 2 factorial. Okay, you remember when we are at order lambda r square, we have to include 1 over 2 factorial. If we were at order lambda r to the n, then we would include 1 over n factorial. Okay, so that is this factor, and this is now that I square gives you a -1. This is a half here. This 4 factorial cancels that 4 factorial, so you get minus half lambda r square ddl over 2 pi to the d Okay, so I will define this integral to be I of P1 plus P2 whole square. Okay, and of course it will depend on mr square as well. Okay, so that's the definition. You see, this integral is going to depend on, apart from the epsilon or d, these values, right? Because look at this integral. This is Lorentz invariant integral. So the result will depend on whatever Lorentz objects you can construct out of it. And P1 and P2 are present, but they are present in the sum. Okay, they appear together, P1 plus P2. So, I mean, very naively, you could say it will depend on P1 square, P2 square, and 2P1 dot P2. But it will not depend separately on this, but only as P1 plus P2 whole square, right? Because that is what appears here as a sum. So square of this. And of course mr square, and if you want epsilon also. But let me drop epsilon, it is understood. So good, let's see this diagram. So this is minus half lambda r square I P1 plus P2 whole square mr square. Okay, now let's see this diagram. P1, P2, P3, P4. Okay, let's assign loop momentum like this. It doesn't matter which way you assign the loop momentum. L plus P1 minus P4. Okay. L enters at this vertex, P1 also enters here, and P4 exits. So L plus P1 minus P4. That's what you have. So if you write this integral, the expression for this, you will get exactly all the factors will be same, all the propagators will be the same except for the difference coming here. So instead of L plus P1 plus P2, you will have L plus P1 minus P4 square, right? This one will still remain L square minus MR square. So you get exactly the same thing. And the expression would be minus half lambda R square. The same integral, but the argument will be this time P1 minus P4 square MR square. Okay, that P1 minus P4 is coming because of this one, this propagator, L plus P1 minus P4. Okay, so the same argument which I gave earlier tells you that the result will depend on P1 minus P4 whole square. Okay, so let me write it down here neatly, all the three. So you'll have the third diagram as well, which is this one, and it's obvious that instead of P1 minus P4, you'll get P1 minus P3. Okay, you can assign the momenta and check for yourself that that's what you are going to get. Okay, so let me write it down. This will be half I of, so also I want to define that we have already seen that P1 plus P2 whole square is what is called S. These are the Mandelstam invariants. P3 square, this is called T, and P1 minus P4 square, that is called U. Okay, so this is a function of S and MR square and epsilon also. Okay, the order has changed now. I should have drawn this diagram first because that is what corresponds to this one. But anyway, expression is still correct. T MR square I of U MR square. Okay, so we have these three terms, and we should evaluate these. So let me evaluate I of P square MR square. Okay, instead of choosing ST or U, I'll just write P square, where later I will put P square equal to S and T and U, and then add these things. So this is DDL over 2 pi D okay, I'm just writing P now. Okay, now introduce Feynman parameters so that we can combine these two integrands into one. Okay, so this I can write as integral 0 to 1 dx1, integral 0 to 1 dx2, delta of x1 plus x2 minus 1, integral d dl over 2 pi d, and then you have I square, I into I makes I square, times x1 of L square minus mr square plus epsilon plus x2 L plus P whole square. Okay. Plus x2 L plus P whole square minus mr square plus epsilon. And you have to square it. Okay. And the other factor coming from the gamma is 1 in this case, because you have only two denominators. So gamma n minus 1, that gives you a factor of 1. Okay, now you should integrate over x2, okay, because there is a delta function, that integral is easy. And okay, and that will just leave behind only x1, which you can then use to write the denominator as the following. So check that the denominator will be this: L square plus 1 minus x1 p square plus 1 minus x1 2L dot p minus mr square plus epsilon square. Okay, that's what you'll get. Now you can redefine x to be 1 minus x1. Okay, and then do the integral, change the variables, and you'll get the following. So after a little bit of algebra, you will find the following. Okay, now we should do what? We should complete the square. Okay, so let's complete the square. The denominator you can write as this denominator you can write as L plus xp whole square. You should check that this is something you can get. P square minus mr square plus epsilon. Okay, now we should shift the momentum, and we are allowed to shift the momentum because we are taking d to be sufficiently small that the integrals are finite. Okay, so I'll then use that and define k equal to L plus xp, or we can write it more explicitly like this. Okay, with this the denominator becomes k square plus x1 minus xp square minus mr square plus epsilon whole square. Okay, this is what you get after the shift. So what's the integral I now? So I is integral 0 to 1 dx ddk over 2 pi to the d, and then you have I square over k square plus x1 minus x p square minus mr square plus epsilon. Okay, Now we should use the formula that I had written earlier. So use integral d dk over 2 pi d 1 over k square minus delta plus epsilon to the capital N is okay. This is the result which I had obtained earlier. So in that I should put capital N equal to 2 and what? And delta to be mr square minus x times 1 minus x p square. Okay, because here delta has a negative sign in front of it. Okay, so using this I get I to be this factor phi square. Then you have I coming from here, then minus 1 to the 2, which is 1, and you have 4 pi d over 2. Then you have gamma of 2 minus d over 2. Okay, capital N is 2. So this thing over gamma 2. And then you have integral 0 to 1 dx. And 1 over mr square minus x 1 minus x p square minus epsilon. Okay, this entire thing to the 2 minus d over 2. Okay, so that's what we get, and you see that you get a simple pole from here. Okay, so let's extract that pole. We are almost there. So 4 pi to the 4 minus 2 epsilon over 2 is 4 pi square times 4 pi power minus epsilon. Okay, and gamma of 2 minus d over 2 is gamma of epsilon, and gamma of 2 is 1. Okay, so with that I get I is equal to minus I over 4 pi square times, let's expand the, what has happened? Okay, so this I square, this minus 1 square is 1, this I square is minus 1, so minus I. Okay, so that is why you have a minus I, and this 4 pi square from here. Okay, and this 4 pi to the minus epsilon I'm going to take care of. Yeah, and this is in the denominator, so this will go into the numerator. It will become 4 pi to the epsilon. Okay, so here expanding the gamma around epsilon equal to 0, you will get 1 over epsilon minus order gamma plus order epsilon term. Then you have, coming from 4 pi to the epsilon, 1 plus epsilon log 4 pi plus again order epsilon term times 0 to 1 dx 1 minus epsilon log of mr square minus x1 minus xp square minus I epsilon plus order epsilon square terms. Okay. This epsilon is different. Okay, now all we have to do is multiply all these terms and look at the singular, finite, singular and finite terms and drop the order epsilon terms. So this is equal to minus I over 4 pi square to integral 0 to 1 dx. You should check that this is what you get. So you get a 1 over epsilon. How do you get? When you multiply this 1 over epsilon with 1 here and with 1 there. So that produces the most singular piece. Okay. Then the finite terms. So look at minus gamma e times 1 times 1. That's minus gamma e. Okay. Then you can take the order epsilon term and multiply with the singular term here and with the 1 here. So that gives you log 4 pi. Okay. And then you can similarly multiply this order epsilon term with the pole term here together with this one. That will give you log of this object. Okay. So that's the result I am writing. You will always find this log 4 pi minus Euler gamma at one loop. Plus order epsilon terms. Okay, good. So now we see how the singularity looks like. Okay, for that diagram. Okay, so the contribution of this is now we have to multiply with the factor of minus half lambda square I of S mr square. Okay, that is what this diagram is. So minus half lambda r square times minus I over 4 pi square. So I'll combine it. It gives you I over 32 pi square lambda r square times 1 over epsilon plus log 4 pi minus gamma e and this term minus integral 0 to 1 dx log of mr square minus x 1 minus x s minus epsilon. Okay, this is P1, P2. And then you have this diagram. Okay, let's go back. This one involved P1 minus P4, that is U. Okay, so let's write this. So this is again the same thing. Let me see if I can just copy paste. Let's see, I can do it again. Yes, I can. Okay, good. So here I should have U and here I should have T. So let me do that also. this will be u, and this will be t. Why doesn't it write? Okay, and this is let me draw the diagram differently. Okay, let's draw it the same way as I drew earlier, which was P1, P3, and P2, P4. Okay, looks ugly, but that's what it is. Okay, so I have to add up all these. So let's look at the singular part, or the sum of the three. Sum of all these is equal to see these terms are the same in all the three. Okay, so it becomes 3 times of that. So 3I over 32 pi square lambda r square 1 over epsilon plus log 4 pi minus Euler gamma, okay, plus or minus I over 32 pi square lambda r square times this integral 0 to 1 dx, and then you have all these terms, okay, that you can fill. So good, now we are almost there, except for the fact that I have forgotten one term, which is this. This also contributes, right? This I should include. Okay, so let's write down the contribution of this. Actually, I should not have deleted. It doesn't undo. Shift command C. No. Does it? No. So let me go to the next page, or maybe here itself. Let's see whether it works. So this one. Where is that? So for this one we have minus I. Okay, I think it's a bad idea to write here. Let's go to the next page. So this is equal to minus I mu to the 2 epsilon, okay, lambda r over 4 factorial, and then you have z lambda z phi square minus 1. Okay, you have a z phi square because you have 4 lines coming out, because it's a vertex coming out of 4 fields. Okay, that is the vertex that we had earlier. Let me show you. Here, you see, minus I lambda r over 4 factorial mu to the 2 epsilon and this piece. Okay, and remember this is lambda r square vertex. Okay, good. But then you have to have combinatoric factor which is 4 factorial, because if you look at this vertex and you want to connect this P1, P2, P3 and P4, okay, this one can go to any of the 4, then the second one can go to any of the 3, okay, 4, any of the 3, then any of the 2, then 1. So that's 4 factorial. Okay. And then you also have 1 over 2 factorial, because we are at order lambda r square. okay, in the perturbation theory. So now to cancel the infinities, I require that the sum of this singular piece, let us work in MS scheme, minimal subtraction. I will remove only the 1 over epsilon pole. So this together with the counter term should vanish, okay? And because I am interested only in the pole, this epsilon I can put to 0, okay? So or you can think of expanding it in powers of epsilon, and you pick up the first term, which is 1, okay? And you are not interested in epsilon log mu square term. So then you get 3i, this is what you have on the previous page, 3i over 32 pi square lambda r square 1 over epsilon. Let's see, 3i over 32 pi square lambda r square 1 over epsilon. That is what I have written here, plus this term, which is minus I over 2, that is coming from here, 4 factorials have cancelled. Then you have lambda r, okay, and then here z lambda is 1 to order lambda, so I have only z phi square minus, sorry, z phi is 1 to order lambda, okay, it is 1 plus 0 plus lambda r plus some number times lambda r square. So z phi I am going to put 1, and here you have z lambda minus 1. Okay, and that should be finite. Or because I am working in minimal subtraction scheme, I choose that finite to be 0. Okay, that's in MS scheme. Okay, and from here I can find that so that I goes away, and I get z lambda is equal to 1 plus 3 over 16 pi square lambda r times 1 over epsilon. Okay, you see that with these choices of zm, z lambda and z phi, I can make both the 2-point function and the 4-point function finite. Okay, so let me collect the result here. Zm square was okay. Over 16 pi square 1 over epsilon lambda r, and this one is 1 plus 3 over 16 pi square lambda r 1 over epsilon. Perfect. Okay, so with these choices I can make the 2-point function finite up to 1 loop, and also the 4-point function finite up to 1 loop. Okay, and do I need okay, how about whether I need more parameters or more constant to fix let's say a 6-point function or a 8-point function? Okay, do I need those? I will leave it to you think about it. Actually, we have already talked about this earlier, and then I will continue the discussion in the next video.